Welcome to an example on damped force motion. I do want to mention this exact same problem is solved in a different video where we determine the motion equation by using formulas derived from a previous lesson. In this example though, we'll solve the differential equation using a characteristic equation as well as the method of undetermined coefficients. To begin, a 10 kilogram mass is attached to a spring having a spring constant of 140 newtons per meter. The mass is started in motion from the equilibrium position with an initial velocity of 1 meter per second in the upward direction and with an applied force of big F of t equals 5 cosine t. We're asked to find the subsequent motion of the mass if the air resistance is 90 times x prime newtons. We use a differential equation mx double prime plus cx prime plus kx equals big F of t to model the motion of the mass, where m is the mass, c is the friction constant, which in our case is the air resistance constant, k is a spring constant, and big F of t is an external force acting on the mass. So in our case, m is equal to 10, k, the spring constant, is 140. Because the air resistance is 90 times x prime newtons, c is equal to 90, and big F of t is equal to 5 cosine t. This gives us a differential equation, 10x double prime plus 90x prime plus 140x equals 5 cosine t. We're also told the mass starts in motion from the equilibrium position, giving us x of 0 equals 0, and the initial velocity is 1 meter per second in the upward direction, which indicates x prime of 0 equals negative 1. From here we can divide both sides by 10, giving us differential equation x double prime plus 9x prime plus 14x equals 1 half cosine t. Recall the general solution x of t is equal to x sub c plus x sub p, where x sub c is the complementary solution and x sub p is a particular solution. And now let's work on determining x sub c. To determine x sub c, the complementary solution, we solve the related homogeneous equation, which is x double prime plus 9x prime plus 14x equals 0. The corresponding characteristic equation is r squared plus 9r plus 14 equals 0. Solving for r, we have r equals negative 2 or r equals negative 7. From here, we have two real distinct roots, and therefore we should recognize the complementary solution will be in this first form here, but of course we'll have x as a function of t, not y as a function of x, giving us x of t equals c sub 1 e to the power of negative 2t plus c sub 2 times e to the power of negative 7t. So again, this is our complementary solution. The next step is to determine a particular solution, x sub p. To do this, we'll use the method of undetermined coefficients. So because the right side of the differential equation is 1 half cosine t, we'll start by assuming x sub p is equal to a cosine t plus b sine t. The next step is to determine x sub p prime and x sub p double prime, then perform substitution into the differential equation, and then equate the coefficients to solve for a and b. Let's work on this on the next slide. I've already performed quite a bit of the work. Here we have x sub p prime, and x sub p double prime. And now we perform substitution into the differential equation x double prime plus 9x prime plus 14x equals 1 half cosine t, which I've done here. Also notice on the right I've included 0 sine t so that we can equate the coefficients for the sine terms on the left. The next step is to group the cosine terms and sine terms on the left, which I've done here in parentheses. Simplifying inside the parentheses, we have this equation, and finally we can equate the coefficients. Looking at the cosine terms, we now know 13a plus 9b must equal 1 half, and we also know negative 9a plus 13b equals 0. And now we solve the system of equations to determine a and b, which will give us x sub p. Solving for a and b, we have a equals 13 500ths and b equals 9 500ths. So now we know a particular solution is x sub p equals 13 500ths cosine t plus 9 500ths sine t. So now that we have x sub c and x sub p, we can now determine the general solution. X sub t is equal to, again, x sub c plus x sub p. And now to finish, we need to find c sub 1 and c sub 2 using the initial conditions. Beginning with x of 0 equals 0, we substitute 0 for t and set the function value equal to 0, which gives us the equation on the right. Notice when we substitute 0 for t, we have c sub 1 e to the 0, and e to the 0 is 1, plus c sub 2 e to the 0, which gives us plus c sub 2, and then plus 13/500 times cosine 0. Cosine 0 is 1. The last term drops out because sine 0 is 0. And then we set it equal to 0, and if we subtract 13/500 on both sides, we have c sub 1 plus c sub 2 equals negative 13/500. Before we can use x prime of 0 equals negative 1, we need to find x prime of t, which I've already done here. To differentiate the first two terms, we need to apply the chain rule. From here, because x prime of 0 equals negative 1, we substitute 0 for t and set the function value equal to negative 1. This gives us negative 2c sub 1 minus 7c sub 2. The third term drops out because sine 0 is 0, and we have plus 9/500 equals negative 1. Subtracting 9/500 on both sides, we have negative 2c sub 1 minus 7c sub 2 equals negative 509/500. And now we use these two equations to solve for c sub 1 and c sub 2. Which I've already done. You may want to pause the video and verify this. C sub 1 equals negative 6/25, and c sub 2 equals 107/500. And now we substitute these values for c sub 1 and c sub 2, which gives us the equation that models the motion of the mass. We have x of t equals negative 6/25 e to the negative 2t, plus 107/500 e to the negative 7t, plus 13/500 cosine t, plus 9/500 sine t. Before we go, let's look at the graph that models the motion of the mass. And here it is. Remember, when x of t is negative, the motion is upward from the equilibrium position, and when x of t is positive, the motion is below the equilibrium position. I hope you found this helpful.